All right, I think we're just going to go ahead and get going. You guys got the front row seat for this presentation. So welcome. I'm Ruben Cash. I'm the environmental coordinator for Skagway Traditional Council. I appreciate you joining us this evening. I've got contact information sitting there on the screen. So if anything there, oh, looks like we got another participant showing up. If any information presented tonight piques your interest, Bone, or if you have unanswered questions, please feel free to get in touch with me. You're probably going to get more than you bargained for because I really love this stuff and I could talk about it all night. So just be forewarned. That's kind of how it's going to go. A little bit of housekeeping. We are recording this event. So it looks like nobody's got their camera on. So that means that you won't show up on the recording. But just be aware of that. If you are uncomfortable with your face appearing online, you can switch your camera off. We've all become Zoom experts and we're aware of that nail biting audio that occurs when many people are talking or when background noise overtakes the main speakers. So just to keep things running smooth, we're gonna keep everyone muted during the monologue, the main portion of the presentation here. If you have any questions during this first portion of the talk, feel free to type it into the chat. I'll do my best to address it as they come up, but we will have a formal question and answer period at the end. So hang tight if I don't get to your inquiry during the talk. The Q&A session, when we have this few people, I think what we'll do is we'll go ahead and unmute everyone at the end and you can just ask away the question, or if you're uncomfortable speaking on the recording, you can just type it into the chat and I will respond to it. So we do have a lot to cover tonight, as usual. If you were here for last year's presentation, it's a lot of the same kind of baseline information. I find it's good to have a roadmap though before we head into things. So we're going to start out by offering you that background information on general air quality concepts. And that's going to be helpful in understanding the results of our study from both 2020 and 2021. So we'll start out with taking that big 10,000 foot view of air pollution and how this is defined, how it's categorized. And then we'll zoom in a little bit closer and do an overview of one specific category of air pollution, which is PM 2.5. What its health effects are, some of its major sources, and then we'll move on to cover federal regulations and a description of how we can actually measure this with the equipment that's available. So this should set you up to understand our study and arm you with the information to interpret the results from our study this last summer. Don't worry, I'll walk you through it as best I can. And then I'll follow up with some of my thoughts for the future, and then we can jump into the Q&A. So let's just jump right on in. Skagway Traditional Council's Environmental Department develops its programs to address priority issues that are identified through tribal member input, strategic planning meetings, and tribal council oversight. Air quality was determined to be a top priority for tribal members, and for good reason. I think we can all recognize that potential sources of air pollution in Skagway have the capacity to increase greatly during busy summer months of a typical season. But I think to start out, we need to talk about what constitutes air pollution, right? Air pollution is just a general term that describes particles of various different types of compounds that are released into the air and can be detrimental to human health and ecological systems. According to the World Health Organization, outdoor air pollution in 2018 was associated with 44.2 million premature deaths, primarily through the inhalation of ultrafine particles or particulate matter. That's why we've got the PM sitting up there. And these are particles that can enter the bloodstream through the lungs and cause both cardiovascular and respiratory diseases. So we define these particles in terms of their size using very small increments known as micrometers or microns. So in science, we use the Système International, or SI, the International System of Units. So that makes it easier for comparing data between countries that may formally use incompatible units of measurements, right? France using the metric system and the United States using this, what we call the standard system, So we're gonna just have a little bit of practice first. So get out your graphing calculators and use the conversion chart shown here to answer this very, very simple question. Show your work, and each of you, if you could prepare a 5 to 10 minute presentation to defend your answer under judgment by the group, that would be great. Should be easy to get through this. I'm just kidding. Conversion can be kind of a complicated thing. So I think the EPA came up with a really great visual to kind of be able to conceptualize what we're talking about here. Everybody can picture a grain of sand, right? In terms of its size, it's a tangible but small thing, and it's around 90 micrometers, right? And there's this nice picture of a grain of sand right here, or roughly 1/10 of a millimeter. So human hair, that's another thing that's tangible. You can recognize it with the naked eye. And this measures between 50 and 70 micrometers. Now, when we get down into the smaller stuff, the little blue balls and little red balls, think about when you're driving along the Dai road behind a truck or a coach bus, and there's a cloud of debris that's kicked up by the lead vehicle's tires. Right? This is typically dust particles that are less than 10 micrometers in diameter. These little blue balls here shown kind of wrapped around the human hair. Right? We call the individual particles of matter this size, quite appropriately, particulate matter 10 or PM10. These are inhalable and can certainly cause some health problems by getting lodged into your lungs and initiating inflammation. So therefore, PM10 is the largest size of air pollution aerosols that are regulated by federal agencies. Far more dangerous, however, are the particles that are less than 2.5 micrometers. These are these little red guys here, and you can see them wrapped around the PM10. Right? They're not only inhalable, but in inhaling them and having them go into the little channels inside of your lungs, they can enter the bloodstream. They can be composed of any of hundreds of different chemicals, and they can travel incredible distances from their source because of their size. They're able to stay aloft in air mass for longer than something heavier like dust, pollen, mold, or fine beach sand, right? So concentrations of fine particle pollutants, or PM2.5, are one of the main factors that we use when we determine an air quality index. You know, if you're looking at Weather Underground or any of these other kind of weather station apps that you can look at current conditions, they'll usually have an AQI, and PM2.5 is going to be a pretty major factor in developing one of those AQIs. So scientists have been studying the relationship between particulate matter and human health for a really, really long time. For example, the paper that's here on the left, this is by Xing and friends from the Department of Respiratory Medicine at Tsushao University. They reported that for every 10 microgram increase in PM2.5, hospitalization rates accelerated by 8%, lifespan decreased by 0.35 years, mortality from cardiopulmonary disease and certain cancers increased by 4 to 8%, and mortality from lung cancer specifically increased 15 to 17 or to 27%. Surveys in Chinese cities, this is this upper right graphic here. You can see, if you don't like looking at graphs, along the horizontal axis here is PM2.5 concentrations, and the vertical axis has the occurrence of lung deaths. And they're saying basically for every increase in PM2.5, there was a measured increase in death rates. Lab studies in this bottom right little graphic here, and specifically the top right of the bottom right, these were studies that were done on rats. They showed that lung infection rates in PM2.5 exposed mice increased 4-fold in 24 hours and 35-fold in 48 hours. So we've got some pretty beefy science to back this stuff up. And in addition to this, the tiny surface of fine particulate matter can also initiate a chemical phenomenon known as free radical production. Metals that are adhered to the surface of these tiny, tiny little particles, such as iron or copper, zinc, manganese, and a host of other heavy metals, they can consume antioxidant compounds, and often the chemical reactions of water-soluble particles produce hydroxyl radicals, which can damage DNA and lead to irreversible damage and cancer. Calcium balance in the human body is affected by the presence of free radicals, resulting in decreased cell function, increased cell damage, and accentuated inflammatory response. So the EPA list of health effects from exposure to high concentrations of PM2.5 include non-fatal cardiac arrest, increased severity of asthma, irregular function of the heart and lungs, and premature death in people that have pre-existing heart or lung conditions. Now, environmentally, the most obvious effect of PM2.5 is visible haze, right? But it can also cause ecosystem damage depending on what the composition of that particulate matter is, the chemicals that are actually in there. So if it's some really bad stuff, lakes and streams could become more acidic, right? The nutrient balance of surface water and soils can totally be altered. Canopies of forests and agricultural crops have been known to be damaged. And all of this stuff can severely change the species diversity, nutrient pathways, and the general healthy function of the given system. So Given the dire consequences of exposure to higher levels of PM 2.5, we should probably look at the potential sources of these fine particles. And when you think of PM 2.5, you should just think of the word combustion, because this is a primary source. Anything that is using combustion in order to get something done is probably producing fine aerosols that could enter your bloodstream. The most obvious potential source is from cruise ships, right? According to the McDowell Group, Skagway hosted around 450 ships in 2019 and was expected to see a comparable number in 2020. And these are gigantic floating cities, right? They require a considerable amount of energy produced through burning diesel fuel. And Alaska Public Media estimates that a single ship uses more electricity than Skagway and Haines combined. It's a lot of juice. And so if you have up to 5 ships in port on a single day, this adds up to a whole lot of exhaust potentially, right? But what else in Skagway uses combustion to achieve a desired outcome? Well, let's think about train and coach bus traffic in the summer, right? Moving people around. The infrastructure isn't large enough to host, what, 14,000 people? So we have to keep people moving this way and that, but those trains and coaches, they're burning fuel, and combustion is probably going to result in PM 2.5. There's a population increase that occurs between April and October on a typical year, and many of the seasonal workers in Skagway are going to bring a car, right? Summertime traffic in Skagway is significantly higher than what we see in the wintertime, again, on a typical year. Extra people are also producing more waste, more solid waste, and our solid waste stream ends up at the incinerator. So that's more combustion, more PM 2.5. Wildfires, it's the new summer normal all across the planet. Skagway is not impervious to the effects of smoke, even if they're from far away. Last year, we had smoke drift in from Russia from the zombie fires that were burning there during the summer. We actually caught that on some of our particulate matter machines. So, and then finally, a hidden and kind of complex phenomenon. It occurs way in the upper atmosphere as gases like sulfur dioxide, excuse me, nitrogen oxides from industrial activities interact chemically. And they produce these secondary particles, which, because they're so far up in the atmosphere and they're so small, they can stay aloft and they can travel just amazing distances and negatively affect air quality from afar. So even though we're not looking at major industrial zones in Southeast Alaska, we're not immune to the effects of these activities. These things could come drifting in on different air currents that occur, different parts of the year. So we've established that air quality is an important local issue. We've identified the most important category of air pollution in terms of human health and what the effects are on the body and ecosystems. And we've touched on potential sources in Skagway. So the next logical step would be to talk about what are regulating agencies determining healthy air to be. And the Environmental Protection Agency back in 1970 established the Clean Air Act. This is a body of legislation created to protect public health through the regulation of air pollution sources. Through the Clean Air Act, practical health limits for PM10 and lower, the smaller particles, have been established and can serve as benchmarks when we're conducting monitoring and when we're reporting on air quality. These benchmarks are stated as 2 different metrics. We have a 24-hour average and we have an annual average, and the 2 numbers are different just because we're looking at 2 different spans of time. And these are evaluated by measuring the weight of particulate matter in a cubic meter of air. Right? This makes sense. We breathe in a certain volume of air to our lungs, and the weight of the particulate matter in that airspace will represent its concentration as we're drawing it into our lungs. So for PM 2.5, we measure in micrograms. And these are exactly what they sound like. They're teeny, tiny little grams. And I love having this graphic up on here because that's another teeny, tiny little gram, but incidentally, it weighs 1 million micrograms, right? It's 1 gram. So again, the conversion, I love metric conversions because they're just very straightforward, but one microgram is 1/1,000,000th of a gram. So EPA standards for PM 2.5 are 15 micrograms per cubic meter on an annual average and 35 micrograms per cubic meter for a 24-hour average. So now we've got our standard to compare to, right? But how are we going to measure our PM 2.5? Well, let's look at some of the more traditional ways to do it. Classic particulate matter measurements involve drawing mechanically sorted particulate matter in a measured amount of air through a pre-weighed fine filter. right? And then measuring the weight of the filter after a period of time elapses. Now, if you're talking about millionths of a gram, you can imagine how precise the scale has to be. So you have to have a pretty expensive equipment in order just to do the analysis, which usually means contracting a lab. And the hardware itself to actually get the mechanical separation of these particles, it's also pretty expensive, right? But it yields the most accurate results. This method is typically used when regulatory studies are conducted that require the most stringent quality assurance standards. For example, measuring a specific airborne compound in an industrial setting, right? But besides the steep price, a drawback to gravimetric methods is that they only give the total weight for a given amount of time, right? Such as a 24-hour test. So it allows no insight into what happens at specific points during the sampling period. You just get this is how much weight there was over the time. So this can have a lot of drawbacks. And so some very smart people developed a real-time measurement technology called laser photometry. And the design is really similar to a gravimetric device, right? Pre-sorted particles of a known quantity of air are drawn into the instrument for a specified amount of time. But instead of collecting particulates on a paper filter and weighing it, the air is routed into a chamber where beams of laser light are emitted toward a receiving sensor. I don't know what it is with scientists and lasers, but we love these things. They do a lot of stuff. And this is one of the many benefits of using lasers. Right, particles enter this chamber and they interact with the laser beam, causing it to diminish in velocity and causing it to scatter, called refraction, right? So the reduction of an intensity can be measured and the angle of its refraction can be measured. And so a series of calculations takes these data and estimates the weight of the particles, and voila, we have measured the mass concentration of the specific particle matter size of interest at a discrete moment in time. And so we can continuously take these measurements over long periods to determine a 24-hour or even an annual average. The issue with photometers is that they're relying on visual cues, which can be quite accurate, but fall victim to a central pitfall, which is best illustrated by comparing two objects of similar visual quality, right? Think of two baskets. One's got ping pong balls in it and the other's filled with golf balls. From an aesthetic viewpoint, the two are the same size. But knowing what we know, having the experience that we have, we know that these are two very different objects that have two very different weights. And so we would not assume that the two baskets would weigh the same. But the photometer relies only on visual cues. It has no other information and it's got no brain to think with. So it would make this assumption that these are both the same. So how do we remedy this? Well, we use kind of a mid-level unit called the TSI Dust Track 2 8530. And these are designed to address this issue. We can set a calibration factor, which has been determined through rigorous scientific study to accurately represent the weights of typical compounds in non-industrial ambient 2.5 aerosols. And not only does the dust track measure as a real-time laser photometer, it also has this 3.7 millimeter gravimetric filter cassette. It's built into the unit so we can further calibrate the meter to match whatever conditions measurements are being taken with. And it can be co-located to itself, removing the need for two units to be set up side by side. And while we could just use the unit as a gravimetric sampler, the time and resources required would be unreasonable. And the EPA has determined that the Dust Track 2 photometer operates within an accuracy that's appropriate for our baseline data collection. So, now you know how we're able to measure these teeny tiny little grams of particulate matter in the air. And we're going to move on to talk about the study design for this project. So it was drafted back in 2018. And this was under the assumption that a regular cruise season would take place, right, during the summer when sampling is conducted. Monitoring would begin in April, just before the first ship arrives, so that we could establish that baseline without the influences of the potential sources, and then continue through the season to capture data during the height of activity. The reason that we're stopping here at the end of September is because that's a fiscal year. We've changed that this year. We're not, because we're doing several years in a row. We're going all the way till the last ship leaves and then capturing a little data afterwards. So 3 locations were selected along a southwest-northeast gradient. And this strategy allows us to see whether cruise ship emissions, which originate from the harbor down at the southwest end of the gradient, are more concentrated down here near their source, or if they're distributed evenly throughout the study area, or even if they attenuate as you move farther away from this potential source. We're also looking for the best representation of ambient air quality. And so having multiple locations along this gradient offers a much more robust data set than just a single location would. 3 is even a little bit on the slim side. It would be even better if we had a dozen stations evenly dispersed throughout the study area, but there's funding limitations that kind of prevent us from getting everything that we want. So site selection is really important when we're trying to consider representativeness. So this is a great little aeronautical diagram that illustrates the way that air currents and turbulence can really get wild and stochastic around buildings and even trees, right? And this could skew results. So similarly, if we set up directly by a busy road, the monitor might be recording direct emissions from passing vehicles instead of the ambient air. So ideal placement has required us to use a little bit of trigonometry, ingenuity, and a lot of compromise, because the world is completely random and variables exist everywhere. And with a little plasticity and flexibility, we can get a lot closer to our target. So our first station is down by the small boat harbor, in an open location far enough away from trees and buildings so turbulence would not be an issue. The site is also within view of the harbor master office, which offers an extra set of eyes to ensure the equipment is not manipulated. Station 2 is up here in the middle of town, an open area next to the STC Tribal Community Center, about midway along the Skagway axis. And again, it has the advantage of our staff being able to visually confirm that the equipment is secure. The final station wasn't originally in an open area at the north end of town in view of the homeowner who would keep tabs on the monitor. But we noticed some skewed results from this station in 2020, most likely due to its closer proximity to Main Street and the influence of PM 2.5 generated by those passing vehicles, right? And because of this, we moved the third station over to the revetment along the Skagway River on the corner of 22nd and Alaska, farther from the road and actually with fewer trees and buildings to affect air currents. And this is our favorite unit because of its official name. Dust tracks are owned by STC, right? Numbered from south to north, 1, 2, 3, and they are particulate observers. So therefore this northern unit here is called STC 3PO. And the nerds will understand why that's hilarious. So our dust track unit is known as a desktop model. You can plug it into a wall and sit it on your desk while it collects data from your home or your office or your workspace. But it can also be set up outdoors and run for extended periods of time with a few add-on accessories. Remember that one of our EPA benchmarks for PM 2.5 is 35 micrograms per cubic meter averaged over 24 hours. And this means that to produce meaningful and comparable data, we need a 24-hour test. With the onboard battery system, we can run the dust track for about 16 hours. So we need to extend this. So we need to add an external battery. That's what you see right here. We also need protection from the elements. You can imagine counting on fair weather even in the summertime is kind of a futile affair. So we employ the use of a waterproof environmental enclosure. Now, turbulence can occur in the lee of a building, but it can also occur at the boundary layer of air right along the ground. So we need to keep the inlet of our station above this ground boundary layer at about the level of an average person's head, right? Because this is where the human air inlet is located. And that's what we're trying, we're after how this is affecting human health. So we put the enclosures on a leveled surveyor's tripod to keep it up above that boundary layer and get it in the right location. So we drafted what is called a Quality Assurance Project Plan. We call it a QAP, to ensure that the data collected are gathered in such a way that results are accurate, replicable, legal, and defensible. This document is reviewed and approved by the EPA and includes all the pertinent information about study design, data management, equipment calibration, roles and responsibilities, and all the other critical aspects of the project. EPA quality assurance officers negotiated with us on the sampling frequency needed for this baseline study and concluded that a 24-hour test conducted every other day at each location was sufficient. The reason we can't do it every single day is because of limitations with power. We don't have a permanent power source at any of the locations, so we have to go back and charge our batteries every day, right? So, but it's still because we're capturing enough data points, the data that we do collect will be statistically significant. So we will actually be able to get a robust data set by doing it every other day. It's worked out so far. The QAP also outlines additional environmental data collection protocols, such as temperature, wind speed, cloud cover, which we gather to assess meteorological correlations to air quality anomalies. right? We want to be able to look at a spike in PM 2.5 and see whether there's a simultaneous drop in barometric pressure or an increase in temperature. In this age of data, I think that the more data you can collect, the better. It doesn't take a lot of space up, it's kilobytes. It's no big deal. So all said, our 2021 sampling schedule was set to begin in April and run through the end of September. That's 6 months, right? Sampling would occur every other day for a total of 87 sampling events across 3 locations. Protocol that was outlined in the QAP required about 2 hours of working time every setup for calibration, deployment, collection of variables, completion of field notes, about the same amount of time on breakdown days, packing things up, recording test results, environmental conditions, scheduled maintenance, data offload. For 6 months, there would be something to do every single day. So we established our monitoring locations. We determined the scope of data needed for collection. We trained to comply with stipulations and protocol outlined in the QAP, and we set up a sampling schedule. And it was time to begin final preparations back in March of 2020 when the pandemic hit. And we thought, oh, well, that's it. There's no point. Canada shut down its ports and the cruise season was effectively canceled. So our primary goal of assessing the impact of cruise season on air quality became completely unattainable, right? And then the wheels began to spin. And we realized that there was this really good opportunity for a somewhat controlled experiment sitting right in front of us. So you think about experimental design, right? You want to determine whether or not compost tea causes a plant to grow larger than using water alone, right? And you'd have 2 groups of plants. You'd have a control group and a treatment group. All other environmental variables like temperature and light would be kept at a constant, right? And that's important. It's important to keep those variables at a constant, so keep that in your mind. The control group would receive just plain water, and the treatment group would receive compost tea. And then after a time, if things photosynthesizing, sucking up water and doing their little plant things, you could compare the 2 groups of plants. And if the treatment group was larger, knowing that all other variables were the same, you might then conclude that there is sufficient evidence to support the claim that compost tea positively affects plant growth. And you would have the data there to support all of that. And this is easy to do in a controlled setting like a laboratory, right? But in a real world setting, this is much harder to achieve. Skagway's air quality is affected by numerous variables, right? Not just our sources of PM 2.5, but what about the wind? What about the temperature? What about the humidity? All of these things can affect the way that PM 2.5 is measured. Our goal is to evaluate the impacts of tourism on PM 2.5 here. In a perfect controlled experiment, we would measure air quality in both the presence and absence of a tour season under identical environmental conditions, right? 2020 offered us the opportunity to capture a pseudo control group for air quality in this snapshot of baseline community contribution to PM 2.5 that would otherwise be impossible to isolate from the background noise of a typical season. However, the thing to keep in mind is that environmental variables are not something that we can control, right? One summer might be hotter or rainier or more or less windy than the next. So even though we did have this great opportunity, there are still variables that are affecting things. We couldn't do this perfect controlled experiment like we have here with the plants. So anyhow, then came the summer of 2021, right? We got 2020 in the bag, got all that data, and that was good. And summer of 2021, first seemed like it was going to be another wash, right? But then it blossomed into this scaled down version of a typical season, what I like to refer to as cruise season light. Capacity was at a fraction of the norm, allowing us to capture half of a summer of that more isolated community contribution, and then another half with a minimal amount of potential sources. Remember, not just from the ships themselves, but also these other associated sources like coach buses, trains, seasonal workers in their car. And these were all in smaller numbers as well. And we're really hoping that next year will pan out as predicted with a fuller complement of ships and many more passengers, not just for the livelihood of the community, but also to round out this data set that we've already collected and to help us answer our central question: does activity from a typical cruise season have a detrimental impact on air quality in Skagway? That's what we're here to find out. So now that you have a good overview of the study design, we thought it would be informative to see what a typical setup looks like. So we're going to switch things over here just for a second, and I'm going to hand things to our environmental assistant, Colton, who is our air quality expert. He has set up so many of these stations and has done so much work over the last 2 years. He's been involved in both studies. So he's going to show you our equipment and walk through a standard site setup. So hang on just a second while we get this switched over. hopefully our camera battery is fixed up, and we will see you in just a second.
So, hello everyone. Tonight I'm just going to be walking you through our setup procedure and how we do our best to ensure the most accurate readings that we can get. So, this is our machine. We have 3 of these, and at the start of each setup day, we'll go through, we'll turn all 3 of them on and make sure they have good battery percentages and that they have no problems turning on. And after ensuring a good startup, we will assemble our assembly plate, and that just screws together. And then we can go ahead and plug that into our machine. And then using this, we will calibrate our machines. We calibrate using LPM, which is liters per minute. We like to target them between 2.8 and 3.2 LPM. And we can kind of keep it in range by connecting these together. And then there are settings inside that we can kind of adjust the range that it's currently in, just to make sure they're all having the same kind of intake values and are in the same range of readings. And then after we have everything calibrated and looking good, we'll pack everything up into this case, and we will head out to each of our 3 sites. And upon getting to each site, we will split up. One of us will take over the machine, one of us will take over the tripod and the notes. And we take our notes in one of these weatherproof, right in the rain notebooks. And when we're taking notes, we look at a couple things. First off, starting in the lab, we will take notes of how well it's started up, if it started up good, if the battery is good, and then we will take our calibration readings and who did the calibration. And then on site, we are looking at temperature, wind direction, and the severity of the current, wind speed, rain, cloud cover. And then we will take notes of anything in the area that might impact results, like construction, tourism, anything like that. Then coming back to the machine, we will start at our enclosure over here. This helps protect the machine from weather, from anyone to kind of tamper with it. And we'll start by screwing this into the top. And this helps block out moisture and helps with air intake. And that just screws into the top. And then on the inside, we have this tube for air intake to the machine. And then we have this bottle that just collects excess moisture. And that all screws in super easily. And once those are all in, we can go ahead and put in our external battery to help keep the machine running for the 24 hours our tests run. And that just goes in and secures, and then we connect the battery. And then coming back to the machine, we have the 0 calibration tube. It's another calibration. Unlike the first one, this one is automatic. It takes a minute to run. We just plug this into the top and tell it to start the 0 calibration. This helps zero out the particle counter to prevent it from drifting into inaccurate readings. And then while this is running, we will disassemble our assembly plate again. And we hit this with 2 droplets of this oil, and then we just reassemble it. Wait for our 0 cal to be done. And that goes on. And then once our 0 calibration is done, that is also noted in our notes that it has completed, and then who oversaw the 0 calibration. And then once that is all assembled, we can go ahead and slide this into our enclosure. And that just slides in and secures in place. And we will connect the airflow tube and connect the external battery. And then after ensuring that is all in, we will switch it over to a survey mode. The survey mode lets us see what the current readings are at for our site. And we can kind of see if it's anything to be concerned about immediately. We can see if it has any errors reading. See if we have to do a calibration again. But if that all looks good, we will switch it over to its actual test mode, start it, let it run for the 24 hours. We'll double check everything is secured and where it should be before we close the enclosure and lock it for the day. The next day, we'll come back after 10 a.m. That ensures that it's run for the full 24 hours. And we'll once again take the same notes and same environmental notes if anything's in the area. But we're after we write down the minimum, the maximum, and the average readings over the last 24 hours. And then what its battery remained at to see if the batteries are still good. And then we're done for that site. We'll go on to the next site. And once all 3 sites are disassembled, we'll come back to the lab and take our machine. All the batteries will go to their various chargers. Everything has a home. And then with our machines, we'll take our assembly plate, we'll unscrew it. Both halves will get washed out with a Q-tip and rubbing alcohol. And then our little plate in here will be allowed to soak in rubbing alcohol for a little bit and then rubbed off. And then all the pieces will be left out to dry until our next test the next day. And then that's that piece. And then our machine itself will be hooked up to the computer. We'll offload all the files off of it. We have various backups. Each file has a home. We'll make sure everything is safe where it should be. And then we'll wipe the machine just to help it so it doesn't get too crowded with data, to prevent any data mishaps. And then we'll swap its battery in with the old one to charge. And then we'll have everything put away for our next test tomorrow. And that's it for our setup and takedown procedure.
Awesome. Thanks, Colton. It's an awful lot of work. We definitely go through a whole rigmarole during the summertime. It is definitely something. So let me switch back to my screen here. Share. All right, pretty cool. We thought that you guys might like actually seeing that whole procedure. There's a lot that goes into it. And you guys have gotten a whole lot of background information, but I'm hoping that all of this is going to help you to understand the test results, which I'm going to kind of go over now. So over the last 2 years, we've gone through that process that Colton just showed you 527 times at 3 locations over 6 months each season. We've analyzed more than 2 million liters of air. We've collected nearly 800,000 individual samples, recorded more than 6,000 environmental observations, and completed around 2,600 calibrations and quality assurance checks. It seems like a lot of work paying attention. So all these data, I forgot to give you the results page. There's all of our machines set up there in the environmental lab, ready to go. So all these data were recorded in that field book Colton showed you, right? And then we digitized them into a spreadsheet. And what I'm showing you here is the Excel page for Station 1 at the Small Boat Harbor. And when we have data in this format, we can mix and match different columns to create graphs that assist in visualizing trends and correlations. And we can also export the table data into a statistical platform such as R to run more sophisticated tests, right? This latter analysis has not occurred yet because there's a tank full of salmon fry that's kept my department busy since August. I mean, really since January. But this is going to be a great January activity. I'm really looking forward to actually running the formal statistics on this stuff because there are a lot of different things that come into play. But let's just look at some graphs and kind of take a simple look at what the data say. This is a graph that just shows the 24-hour average concentration of PM 2.5 at the Small Boat Harbor for the entirety of the study period, recorded in milligrams as opposed to micrograms. The 2020 data are shown in gray, right? And the 2021 data are shown in black. This red line here shows the 24-hour EPA benchmark for PM 2.5. And as you can see, this location mostly remained well below the regulatory limit both years, even with data that still hasn't been adjusted for ambient 2.5 calibration. Remember I said there's that calibration factor. So you see this spike here that does dip into the 0.35 or 0.035 range, but this is actually going to be closer down here to the 20 once we calibrate it. So all of these data are going to get kind of squished down. So that's great. I mean, we're below the benchmark, and we had clean air, and I'm sure you guys are all thinking like, well, yeah, we had clean air. Of course we had clean air. We hardly had any ships. But remember, our CRAP makes these data legal and defensible. So we can confidently report that community contribution to PM 2.5 in the summer of 2020 and cruise season light during 2021 at this location generally did not exceed the regulatory limit established by the EPA. And that's great news. And if we look at all three stations simultaneously, we can see that this was the case at all locations, from the harbor up here on the left to 21st down here on the right. Right. I was surprised, though, to see very little apparent differences between the 2 years, right? And definitely no obvious change between the first and the latter half of 2021. I was expecting to see lower numbers down here and higher numbers over here. There's a lot of noise in the data. So let's shift to a new visualization, right? This is just the average PM 2.5 at the Small Boat Harbor in 2021. Just a single data point, right? And it doesn't really give us a lot of information. That's what, like 200 and some samples all averaged out into one, right? Not a lot of information. So statisticians like to use what's called a box plot. This is a box plot. And this gives us a whole lot more information about the data than simply just looking at the average. The box contains the middle 50% of the data points, right? So half of the data lies within this box. And then each line, which are known as whiskers, represent the remaining 50%, the lowest at the bottom and the highest at the top. The X right here marks the average, and the line marks the median, which is the middle value above and below which lie the top and bottom 50% of data points. So when we look at data this way, we can see how much variation there is, the distribution of the data along the continuum, and we can simultaneously also see the average and any outliers, right? You see that this point up here, this was not included in this computation here because it lied so far outside of the standard deviation that it was not included in there. So here is a box plot graph showing PM 2.5 data from both years. They're paired by site, right? So we can directly compare the control group to cruise season light, right? So 2020 is right here at the Small Boat Harbor, and 2021 at the Small Boat Harbor is here, right? STC 2020, STC 2021, 21st 20, 21st 21, right? Doesn't look like there's any really obvious differences as expected, but remember, these are averages from the entire season for each year. So we only had ships for the last half of 2020, right? So it's averaging out. It's kind of an inaccurate comparison. Really, to have a box plot next to 2020, we should have a full cruise season here. We would probably see a lot more significance, right? Anyways, without thinking about that too much, there could still be some environmental clues to explain why both years appeared so similar, despite the last half of 2021 having a small contingency of ships in port, right? So wind can have a significant effect on PM 2.5 concentrations, and this makes sense intuitively, right? More wind means more air movement, which would then tend to transport particulates and replace them with fresh air with less particulates in them. So these are real-time data from 2020. And notice these are from our 3 sites. This is July 30th, 2020. This is, oh, I skewed these. This should be up here. Anyways, so we have the STC site. This is the small boat harbor here, and this is 21st. Notice how in all 3 of these, the beginning of the sampling period, you have some pretty elevated aerosols. I mean, up in the 45 microgram range. This would have been above the regulatory limit if it had stayed this way. And it's the same in all 3 graphs. And just for a little bit of context, this was absolutely dead calm in the first part of this day. Between 9 a.m. and 3 p.m. there was no wind, 0 wind. Then all of a sudden, just after 3 o'clock, a really stiff south wind kicked in and basically maintained itself for the rest of the day. And you can see here where those aerosols attenuate and go down to nearly 0 and then stay pretty low for the rest of the day. So that's that significance of wind. We noticed it on several of our tests. So let's look at a box plot showing the wind. And again, these are sites paired by year, Small Boat Harbor 2020 and 2021. It sure looks like the median, at least at Small Boat Harbor, the wind was a little bit greater, but at the other 2 sites, they were virtually the same. So perhaps wind doesn't alone explain our data. Temperature averages, this is another box plot showing temperature averages and medians. And you can see, I mean, really, there's not really a whole lot of difference. There's a little bit of a downward trend from 2020 to 2021. It might be a little bit colder. Statistically, I don't think that you could make that claim. And higher temperature can have a greater capacity to hold moisture, right? Which might overestimate particulate matter, since the photometer has a hard time differentiating between water particles and other aerosols. You know, it's the whole golf balls, ping pong balls thing, right? So we can also see that 2020 had more days of rain than 2021. I think you can almost assign statistical significance here. Probably not until the formal statistical analysis is done. I'm not going to make any claims, but this adds to the potential for overestimation. But keep in mind that we're not recording continuous observations of environmental variables, right? We're recording that discrete moment in time when the equipment was being set up. So really, you need to have a weather station at each one of these stations to be able to get very, very robust data to back up any theory that environmental variables are affecting. More reliable metric for understanding moisture in the air is relative humidity. And this is recorded at the airport hourly. So I've broken these data into paired years by month, and the box plots are somewhat all over the place. You know, most of the months were more humid from 2020 in 2021 than they were in 2020, right? But some were less. But my suspicion is that we're not going to be able to weed out any trends that are related to environmental variables until a much more sophisticated statistical analysis is performed, looking at several metrics simultaneously. So it's just going to take some time to really get to the bottom of it. But we were able to pull some significance when we looked internally at 2021 isolated from the larger data set, and then pairing that analysis with actual ship data. So here we are looking at PM 2.5 averages on days with no ships on the left-hand side and days with ships on the right-hand side. And here, because the medians are outside of the box, and it's not highly significant, but it is enough to assume a little bit of statistical significance, right? So here, this is at the Small Boat Harbor. This is at STC, same story, a little bit more variation in the data. And finally, here's the northernmost station. So a little bit higher. Remember, cruise ship light, we didn't have a lot of boats, but we did start to see a little bit of this upward trend. So looking at this chart, and we now have the familiar 2.5 concentrations on the vertical axis, right? And a number of ships from 0 to 4 along the horizontal, right? And you might be trying to remember when in 2021 we had 4 ships in port on a single day, and don't question your sanity. They were never in quadruple at the same time, but we had several days where the sampling period bracketed 2 pairs of ships, right? One set leaving at the middle of the effort and then another arriving right at the end. And here we can see a pretty clear upward trend at the small boat harbor, right? Compared to no ships, it seems like the more ships that there were, seems like it kind of eked up just a little bit. So if we move north to the STC location, the trend's still there, but there's a lot more variability in the distribution of the points. Not so confident in how much of a trend there is. And then finally at the northernmost station, the trend is weak. It's still kind of visible, but it's not as cut and dry as as you would hope it to be. But data is data. So this brings us though to kind of the final commentary. If we're looking at these, it attenuates. It seems like there's a clear pattern closer to the harbor, and it kind of disintegrates as you get further away. So is there evidence that air quality is worse near the principal sources of the harbor and better further away? These last few graphs could support this hypothesis, but let's look at some raw data to see if there's any more clues. This is real-time data from August 16th, the small boat harbor, and one of those sampling periods that bracketed 2 pairs of ships. And we can see that there are elevated aerosols occurring kind of right here at the time the ships were in port. Up to the time that they left, there's some attenuation. And then this kind of curious stepped overnight rise, followed by a spike in the morning, right about the time that the ship would show up, right? I'm not sure, I haven't actually looked at the wind data, but I'm wondering if it's possible that we are seeing kind of a gradual arrival of aerosols as the ship made its way up the canal. It's hard to say, but I think what's interesting though is looking at the same day at the STC, right? You see it's kind of the same pattern, but things are just a little bit, like the edges are taken off it. It attenuates just a little bit. And then look at the same day up at the north end of town, right? It seems like what we're seeing here is possibly closer to the source, we're seeing more concentration of these aerosols, and the farther away you get, it seems to go away. So at any rate, there you have it. Summer of 2020 provided us with those results for the control group of our study, and summer of 2021 gave us the opportunity to slowly introduce PM 2.5 sources and see how it affected ambient 2.5 levels around town. But what this means is that our experiment is really only still partially completed, right? We're already preparing for next summer's round of sampling. Hopefully we have more ships. Our dust tracks have to be recalibrated. The maintenance supplies have to be required. Our crop needs to be updated, and there's all sorts of fun work to do. But what else does the future hold? Well, we're hoping to work some more with the Park Service. We're hoping that they're going to continue doing some of the work that they've been doing over the last several years, right? Many of you may be familiar with lichen study, right? Which permanent arboreal macrolichen plots were sampled for elemental analysis, right? When we're looking at particulate matter, we're only looking at the presence of aerosols. We're not looking at what they're composed of. The Park Service is filling this gap by looking at these macrolichen plots. So they take samples and they send them into a lab and they look at the different heavy metals that are in. And then in partnership with the municipality, Park Service also collected data on nitrogen and sulfur compounds at both Lower Dewey Lake and Saintly Hill using 2 different methods. They use these passive samplers these are ambient atmospheric pollution samplers every 2 weeks over 4 summers. And then these bottom ones are called depositional, what are they called? Ion exchange resin tube precipitation collector arrays. I want one of these for my place. They look really cool. And these are looking at total deposition from spring until fall. And these 2 methods were employed during 2008, 2009, 2018, and 2020. So the park has data for nitrogen and sulfur compounds from both a typical tourist season and this outlier summer of 2020 without cruise ships. STC and NPS have been discussing possibilities for collaboration, and we're still hoping to partner in air quality studies in the future. What I'm most excited about is the possibility of implementing a more permanent photometer monitoring network that runs 24/7. Remember how I said it would be cool if we had 12 stations set up all throughout that Skagway axis. These are they operate, purple air monitors operate much the same way as our TSI dust tracks, but they're a fraction of the cost. So we just need to find out how data from the 2 units compare, right? If it's comparable data, we could look at whether there are significant discrepancies between data sets by setting them up side by side. If it's found that they're comparable, this network could be established and an AQI could be developed along with possibly a warning system that could alert Skagway residents of an air quality event taking place, right? You get a forest fire coming through and the smoke comes through town. If we've got this network that's actually ticking down data every single day, we could actually issue a warning for residents to stay indoors, especially if they have respiratory issues. So that's kind of what we're looking at. Thanks for sticking with me for the whole hour. It's a lot of talking, and I'm happy to open it up for questions. With this small group, I'm basically just going to ask everyone to unmute, or you can type it into the chat, or we can just call it a night. I'll leave it up to you all. Stop the share.
Just saying thanks, Ruben.
All right, thanks for joining us, Donna.
Yeah, Pete's here too.
Oh, hey,
He said-
Pete.
And yeah, good job. Very thorough. Looking forward to what happens next year.
Yeah, me too. It'll be very interesting.
I'd like to say thanks, Ruben and Colton. Very informative, and I think this is a great opportunity to be able to collect this information this year. And I'm glad you guys are dedicated to it.
Yeah, we sure are. Especially this guy Colton's he's a trooper, man. He did a lot of the sampling efforts. He's put in a lot of hours behind those machines. So I got to give him a round of applause for everything that he's done. Like, at least half the data was collected by him.
Excellent work. Yeah, Courtney was just saying that she's never seen anyone tending to those boxes. I said that's because they always do it before 10 a.m.
Yep. Yeah,
I think.
we try to.
So thanks a lot, guys.
All right.
Have a good night.
Thanks, you guys too. I guess we'll call that an evening. Thanks for joining us, and we'll see you at the next one. Hopefully, we will have more answers on all of your burning statistical questions. So, yeah, everybody have a fantastic weekend and a lovely holiday, and we will talk to you all later.
See ya.